we are live. Excellent. Welcome. This is going to be an interesting, fun experience for us all. For those of you that don't know, I do have a better live streaming setup at home than I do at school. Now, you might be like, "Oh, but Mr. Markey, look, there's still a glare there." I know there's still a glare there. I mean, that glare goes away when I actually like start putting like pieces of paper underneath here and stuff like that. Gotta clean that. There we go. But I can do all sorts of things. Like I can show you various websites that I'm working on. I should change the size of this. Let me change the size of this, make it a little bit easier to see. I can do all of this all in one shot. It's really nice. Yes. So then it's like, hey, I can flip to here's your Google Classroom, for example. You know, um, here's the live streaming service that I'm working off of, something along those lines, where I can see you guys in the chat and things of that nature. Um, here's a wide shot of me. Like just stuff like that. Um, I do various setups when or I can do like a back in 5 minutes setup, or I'm coming, starting soon setup. I can do all sorts of stuff here. It's so much fun. But I have all sorts of different things that I do for this. This is the system that I use for live streaming video games, which is just oh so fun. So, good morning to those of you in the chat. I'm going to get started in a few minutes. I'm just allowing people to kind of filter in because of the strange circumstances that are surrounding our lives right now. As I've been saying for a few weeks, I am going to continue as normal. I know that some teachers are like, oh no, I couldn't get my stuff. Oh no, I can't live stream today. I'm a live stream regardless because I'm going to do my job. That's what I do. For the 9 of you that are in here right now, I see Paul gave me a good morning. Well, where's my good morning for everyone else? I don't know. I'm just saying. It's like, hey, it should all be like, oh, good morning. Oh, we miss you. Oh, we wish you were back in class or something like that. Oop, I think somebody's trying to turn the doorknob. Yeah, there she is. Hold on. Come here. Come here. Come here. Oh, goodness gracious. So, for those of you that are interested in seeing, hold on, let me change the widescreen shot. Let me turn this down. There she is. There she is. She thinks it's the funniest thing ever. You can see yourself. Say hee hee hee. You're okay. All right, you're gonna go back with Mom now, okay? Okay, say bye-bye to everyone. There she goes. Okay.
Come on. Let's leave Daddy be, okay?
Oh, it's so much fun. Top down. So that was my daughter. So oh goodness gracious. My personal YouTube channel. Hold on a second. I can get to my personal YouTube channel here in a moment. There it is. If you're interested in my personal YouTube channel, how do I share this particular screen? I don't know how to do it. Let me copy. I'm gonna cut and paste something into the live stream. So, click. I think that link. Yep, and it works. Should take you directly to my personal YouTube channel. This obviously is my school YouTube channel, but that is my personal YouTube channel. So I know she is. I see all your comments about my daughter. My daughter is the most gorgeous thing ever, is what she is, and no one can tell me otherwise. And yes, she will get away with everything. Everything. when she's older, because I will have no spine for that kind of thing. So, but anyway, I digress. So, here's the plan for today. In Edulastic, I have assigned you an assessment to get done for me. Now, this assessment is in regards to solving polynomials and things that we have been doing over the course of the past couple of weeks. This will be due on Wednesday. I obviously giving this the same assessment to my 8A classes, but I will see them tomorrow. But it is due Wednesday. It is due Wednesday. I'm saying that over and over again because I need you to adhere to the due date as the assignment in Google Classroom obviously specified. I'm trying to think what else, because again, I'm not in my normal setting right now. Obviously, I'm still in a shirt and tie right now, obviously, as you can see. And I have my little top-down setup right here, which is really nice. Let me change this just a little bit. There we go. There I am. This is actually how I live streamed in the spring, which was really nice because not all teachers were live streaming back in the spring. But now I got multiple cameras set up. I got this camera and I got this camera, and it's so much fun. Oh, goodness gracious. I may end up live streaming a video game at some point this week. I don't know when. But you should all subscribe to my regular channel just for fun. But anyway, here's my goal. I want to review what we need to review about polynomials. I need to give you some important definitions, as the title of this video clearly states, polynomial attributes. I want to give you all of the information that you need in order to get this done. So, I'm going to ask for a couple things. Now, obviously, I see those of you that have already commented in the chat. So I'm just going to say, hey, you 13 viewers right there, let me know who you are. Give me a hello. Give me a thumbs up. Let me see who you are. And I'm going to need those notebooks out and open. So you guys do that. I'm going to get set up and we'll get this thing started. There we go. And there we go right there. Good. Now, today is the 23rd, as you can see right there. We are going to call this polynomial practice and attributes, because there's various things that I want to give you. It's going to be nice. It's going to be very nice. There we go. Oh, there are some people saying hello to me in the chat. There you go. Hello, peoples in the chat. Nice. Excellent. 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 And again, for those of you that are wondering, obviously that is my personal YouTube channel that I posted the link to. So we'll get this thing done. So, oh, there's some more people saying hello. That's nice. That's nice. Okay, back to this. So first and foremost, let's talk about example polynomials and what I refer to as the degree. I've never actually formally written this thing down, but I want to make sure that we do that. A couple of examples here. Y equals x squared plus x minus 1. Y equals 3x to the fourth minus x squared. I don't know. Y equals 2x, for example. And one more, y equals, I don't know, x plus x squared minus x cubed. There we go. So I got 4 examples of polynomials right here. Now again, the definition of the polynomial that I have given you is a polynomial where all of the exponents are positive whole numbers. That is just the general idea of a polynomial. The degree, if I could create a little chart right here, which is nice that I can actually do this. The degree of the polynomial that we are dealing with, well, in this case, the degree is 2. And for this problem, the degree is 4. And in this problem, the degree is 1. And in this problem, the degree is 3. But why is that? Why is that indeed? For these types of problems, It doesn't matter the order in which they are written. The degree of a polynomial is the largest exponent. The degree of the polynomial is the largest exponent. Now, again, they have to be positive whole numbers. If you have fractions in there, then by definition you don't have a polynomial. If you have negative exponents, mind you, not negative numbers, but negative exponents, then by definition you don't have a polynomial. So, the degree of a polynomial, given that it's a polynomial, is the largest exponent. Now, what does that tell you? What does it tell you? It actually tells you a few different things. What it tells you, let's call the degree, quote, n. Let's just call it n. So if the degree of the polynomial is some variable n, it could be a 2, it could be a 5, it could be a 10, it doesn't matter what it is, but let's just call the degree n. Let us, I'll put a little apostrophe there for the fun of it. Nice. Then a polynomial will have at most n, quote, quote, real solutions. Let's call the degree of the polynomial n. Then a polynomial will have at most n solutions. Now what that means is, well, if I have a quadratic, for example, and I'll bring my calculator up here. This is the better calculator that I keep at home, better than the one that I have in my classroom. But if I had this, I'll just reset that there we go. And I put in like x squared plus x plus 1 or some junk like that. I don't know. And I decided to graph that. It's a second degree polynomial. The degree is 2, which means it has at most 2 real solutions. Now again, I emphasize the phrase at most, because I'm going to zoom in here. You can see that this thing does not cross the x-axis. It has no real solutions, none. It still fits the definition. Then the polynomial will have at most n real solutions. I could change this to minus 6, changing the polynomial, same degree. Now it has 2 real solutions because it has 2 x-intercepts. Crosses the x-axis twice. That's 2 real solutions. That's what it comes down to. I could have a third degree polynomial like this, x to the third power. I'm just going to keep it very simple, x to the third power. Actually, you know what? No, I'm going to make it minus 8. Yeah, I'm going to make it minus 8. So it's x to the third power and then minus 8. It's a third degree polynomial. It should have at most 3 real solutions. And if you see the graph here, chapow! It clearly only has 1. But it still fits the definition of having at most 3 real solutions, meaning 3 or less. That's what the degree will tell you. Now, the degree tells you a bit more. If you include, quote, complex solutions and repeated solutions. Now keep in mind, complex solutions are when you have to include the letter I. It's the square root of -1, an imaginary. If I don't like calling them imaginary, but that's what they are. Or repeated solutions, which we've seen examples of repeated solutions. I'll do an example with you in a minute. But if you include complex solutions and repeated solutions, then a polynomial will have exactly n solutions. Now, note the difference between what I just wrote and the previous definition. In the previous definition, I said at most n real solutions. Just real solutions. Actual x-intercepts to the graph. Visual crossings of the x-axis. But in the next definition, it will have exactly n solutions. That's, again, if you include complex and repeated solutions. For example, very basic example here, x squared, I want to make sure I do this one right. No, I don't want to do that one. I'll do that one. Yeah. Plus 8x plus 16 equals 0. There we go. And I'll graph that for you in a moment. Let's put that over here, actually. X squared plus 8x plus 16. Let's take a look at the graph. If we look at the graph, oh, interesting. Now, some of you may know exactly where I'm headed with this, which is fantastic. Let me actually zoom in over here so you can see what I'm dealing with. What it looks like is the graph just touching the x-axis once. It looks like it only has one real solution, and that's correct. It only has one real solution. But according to this definition, if you include complex and repeated solutions, he was on his personal account. Sorry, I just read that. But if you include repeated solutions, then it fits that definition, because you could actually factor this into x plus 4, which gives you an answer of -4 and -4. Now that's a repeated solution. It only has one real solution, but if you include repeated, it does have two solutions. It just so happens to be a repeated solution. So these definitions, these attributes that I'm talking to you about, fit for every single polynomial that you're dealing with, and you can tell solely based on the degree of that polynomial. Let me give you another piece of information here. Let's give you another piece of information. Let's see here. I always got more paper. A turning point. A turning point is when a graph changes vertical direction. A turning point is when a graph changes vertical direction. So for example, I'm just going to draw this. I'm going to sketch this out, and I would like you to sketch the same thing. If I was going to have something like this, there we go. This graph has two turning points. It has two turning points. Change in vertical direction. It has a turning point here, meaning before this point it was going up, and then after this point it's going down. That's a change in vertical direction. That's a turning point. The second turning point is over here, where before that point it was going down, and then it changed to be back up. Yes, it would. The question that he asked was, if you were to throw a ball, would the turning point be the max height of that ball? Yes, because in that example, if you're throwing a ball, the path of the ball or the height of the ball would be following a quadratic path. And if you were following a quadratic path, it'd be going up and then it would change vertical direction, and the turning point would be coming down. For a quadratic, now this is specifically to a quadratic. To a quadratic, the turning point is the vertex, and it's always going to be the vertex. Beyond a quadratic, for this example right here, this is not a quadratic, you can't really identify a quote-unquote vertex, because it may or may not have these turning points. Here's the definition. Again, the degree of the polynomial is n. Keep in mind that the degree is n. The degree is n. A polynomial has at most n minus 1 turning points. A polynomial has at most n minus 1 turning points. You can take the degree of the polynomial, subtract it by 1, and at most, the graph would have that many turning points. So for example, look at this. This is the one we did before. This is x squared plus 8x plus 16. The degree is 2. According to this definition, if the degree is 2, then the polynomial would have at most 1 turning point. And you can see right there, it does. Just like what Tristan was saying about the ball being thrown. If the ball was being thrown, I can flip this thing around. Let's throw in a negative right here. There we go. There it is. There's the ball being thrown. And you can see it only has 1 turning point. I could change this thing around a bit. I can make it an x cubed plus x squared minus 3x minus 1. Again, making this thing up. Graph it. Look at that thing. It is a third degree polynomial. And you can see that right there. It's third degree because it's x cubed, the largest exponent. And when you graph it, it actually has 2 turning points. But a third degree polynomial doesn't have to have 2 turning points. It doesn't have to have 2 turning points. Look at this graph right here. Let me zoom in on that spot down there. Let me zoom in on that spot down there, because this is really going to blow people's minds. A turning point is a change in vertical direction. It's a change in vertical direction. And if I'm looking at this particular graph, it's going up, 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 flattens, but up, 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 up. It never changes vertical direction. It keeps going up. At no point does it ever turn back down. This example that you see in front of you of a third degree polynomial, this example has no turning points. The definition says it can have at most that many turning points. So again, just a visual example. You could even go with a linear equation. Look at this linear equation that I got going on here. 2x plus 3. Look at this linear equation. It is a first degree polynomial. By definition, being that this is a first degree polynomial, the definition says that it will have at most 1 real solution. And if you include complex and repeated, it will have exactly 1 solution. And according to this, it should have 1 minus 1. It should have no turning points. No turning points. Think about a linear equation. At any point, does it change its vertical direction? No. No turning points. How many times does it cross the x-axis? Once. That's how these problems end up working out. It's really nice. It's really nice how they do it. Now, let's go a little bit farther now. I want to take this into the realm of division. Let's backtrack to division a little bit. I'm going to take you back to, I don't know, 4th or 5th grade. I don't know what year you first learned long division or some junk like that. I don't care. I really don't care. But let me just give you a basic example. Example of long division. Now, mind you, I'm not teaching you long division of polynomials. There actually is a method for long division of polynomials, but I am not going to teach you long division of polynomials. That would be painful, to say the least. I just don't want to do that, you know. Who is banging on my door? It's probably my daughter again. No, I'm not going to bring her back. Maybe I'll bring her back before the end. No, I won't. No, I won't. Anyway, long division of polynomial. No, of numbers. Numbers. Let's just say I had something like 24. 24 divided by 5. Something very basic. Long division. Now, if I were to do this as you've been taught in the past, okay, you put the 4 up here. 4 times 5 is 20. You subtract, and you get a 4. And you'd say, well, it's 4 remainder 4. One way of writing the answer is saying 4 remainder 4. But I don't want to do that. Now, some people have been taught, well, Mr. Markey, if you add a decimal point after the 24, I should say, if you add a decimal point to the 24 and the decimal point here, you can continue the long division. You can. You can continue the long division. And if you continue the long division, you can get the decimal. And some people would do that. And the decimal would actually be 4.8. But that's not what I want to do right now. What I want to do is actually what long division was actually intended to do, which was to give you the resulting fraction. Because sometimes if you do long division, that dividing and getting the decimals could go on forever. So instead, we write the answer like this. The result, or the answer the way that I want it, the answer I want is 4 and the fraction. Now you got a remainder of 4. A remainder of 4 divided by 5. It seems strange, but that's the way that I want to write it right now. Let me show you another example, just as a comparison. I don't know. No, I don't want to do. Yeah. I want to do 3. Okay, good. 26 divided by 3. Excellent. We'd put an 8. 8 times 3 is 24. You would subtract and get a remainder of 2. But I don't want to write it like that. I don't want to write 8 remainder 2. I don't want to write 8 point and then get the decimal, which by the way would be 8.6 repeating. I don't want to do that. Instead, I would say the answer is 8 and this 2 divided by 3. That's how I would write that answer. Now, this is not your typical way of writing answers like this, but the way that you're writing these answers are going to relate to what we're doing with polynomial division. Let me show you what I mean. What I mean is something like this. Let's say the example that I gave you, something very basic, was like x squared plus x minus 6, one of the most basic examples that I typically do. But this time, I am going to divide it by x plus 1. I'm going to divide it by x plus 1. Now, in this example, I'm going to take a sip of my coffee because it wouldn't be a class with me if I wasn't taking a sip of coffee. There we go. Wonderful. If I was going to do this, I would go back to our synthetic bar. Now watch what's going to happen because you're not going to get a 0 here. I'm going to go back to the synthetic bar. It's a 1x squared and a 1x. So it's a 1, 1, and a negative 6 right there. Now I'm dividing by x plus 1, which is the possible factor, but I can't put x plus 1 here, and I'm not going to put a plus 1 there. For those of you who know from what we've been doing the past few weeks, you would have to put a negative 1 there. And then we continue with synthetic division. 1 plus nothing is 1. 1 times negative 1 is negative 1. 1 plus negative 1 is 0. 0 times negative 1 is 0. Add them together, you get negative 6. Now, I've always referred to that number as my remainder. And the goal of all of these problems has been to get a 0 in that spot. That's pretty much been my goal from the beginning. But now, for this problem, that's not what it's really asking you to do. What it's really asking you to do is saying, okay, I want to divide these, but now I got a remainder. Ugh. Sometimes this happens, and I want you to be aware as to what you actually have to do about it. So, this is your remainder. This is your constant. This is your x, the way it's always been. The way it has always been. So technically, this is a 1x plus 0, so I don't really have to do the plus 0. But then I have to deal with the remainder. In the past, we would always, or we would try to get a 0 as your remainder. We would try to get a 0 as the remainder. But sometimes that doesn't happen. And sometimes the problem's like, hey, just divide these. See what happens. Now, if you got a remainder of 0, then the top of this fraction would be 0, and it wouldn't even be there. It would just go away. Goodbye. So long. See ya. That's what this thing does. It's very weird. It's very strange. Let me see just one more example of this. And then I want to take you on some polynomial examples that you're going to need for that edge elastic assessment that we're doing. Let's see what we got going on here. Because I have you guys until technically 10:28, and that would be the remainder of third period. I know, right? I love the setup that I have at home. It's so great. So one more weird example, just dividing these things out. I don't know. Let's say like I had an x cubed minus 2x squared plus 1 divided by x minus 4. Just making that junk up, I don't know. And I gotta divide these two. So, I'm gonna set up a synthetic bar. Now, I did this on purpose, there's no typo. I'm missing an x term. I am missing an x term, which means that if I'm gonna do this correctly, I gotta put a 0 in that spot. I have to. X minus 1. X minus 4. I got to put a positive 4 on the outside right here. Because that's the possible 0 that I'm trying to solve for, or whatever. I don't know. Now, again, I know this is not going to work out. I set up this problem where it was definitely not going to work out because I wanted to get a remainder. I just wanted to show you what would happen if we divided by something that wasn't going to work out nicely. And I'll talk about what that actually proves after the fact. 1 plus nothing is 1. Multiply by 4. Add the two of them together. Multiply by 4. Add the two of them together. Multiply by 4. Add the two of them together. Synthetic is complete. Now again, this is your remainder. What this proves is 4 is not a 0 of the function. What this proves is x minus 4 is not a factor of the problem. Sorry, I'm distracted by my wife. She was putting the cat into the bedroom because apparently the cat wanted to get in the bedroom and was making too much noise, and now it's a distraction to me. There's my cat. Hi, kitty. Oh, yeah, you just keep, scratching yourself. Whatever. I don't care. Anyway, but that's what this thing proves. It proves that 4 is not a 0. It proves that x minus 4 is not a factor. It proves it. Proves it. The answer of this division, the result of this division, we can still write out. It's just that 4 is not a 0 and x minus 4 is not a factor. Remainder, constant, x squared. So this would be a 1x squared plus 2x plus 8 plus your remainder over what you divided by. Technically, that's how you would have to write out that answer. It's very strange. I know, very strange. But that would be the result of the division. I know. So let me see. I hit all of those. Expected result isn't 0. Good. So let's try some examples. After this class period, I'm hoping that you guys are going to, well, after school, really. I mean, you still have 4th period to do. But given the time that you have, after school, tomorrow, things of that nature, I don't know, you do have an Edge Elastic assessment for me. That assessment is live right now, and it is on everything that we've been doing in the past few weeks with polynomials. And what I would like to do, with the time that I have left is I would like to go over some examples. For the record, ASMR videos are the creepiest, most unintelligent things I've ever seen on the internet. It's more unintelligent than people getting millions of views for opening up boxes of Pokemon cards. I said it. Just saying. I don't know. Alright, so why did they let me do this? Let's see what kind of example I got for you. Okay, so for example, and this is reviewing specifically for just everything we've been doing with polynomials up to this point, because there's still more that we got to do. Yeah, I know. So here's the example. I might have something like f of x equals x cubed plus 3x squared minus 12x plus 7. And I may ask you to evaluate f of 3. I may say evaluate f of 3. Now this is the other thing that synthetic division or synthetic substitution actually does for you. What's really nice about it is that it allows you to do this substitution in such an easy, nice way. Now this particular problem doesn't really have too great of a solution. But again, that's not what the problem is asking you to do. I'm just kind of looking at the polynomial right now. This is what the polynomial looks like. And none of it looks good. None of it. It just looks absolutely terrible. But that's not the point. The point of this particular problem that they've asked you to do is to evaluate it at f of 3. And you could do one of a couple things. Number one, you could take that 3 and you could plug it in for all the x's. Or a faster way of doing this problem would be by using this synthetic bar. And the result of the evaluating would be whatever number you get down here. It all depends on what the question's asking, but the synthetic bar allows you to do all of it. Now, I'm not saying that you have to do it this fast, but you could do it this fast. I don't know. 1, 3, 6, 18, 6, 18, 25. Done. You don't have to do it that fast. I'm just saying that you could. You could. Absolutely. Now, what this means, clearly 3 is not a 0. Clearly x minus 3 is not a factor because we didn't get a 0 down here. But that's not what the question was asking. The question was asking you to evaluate it. What is f of 3? It's 25. The result's 25. The result of substituting this 3 into the problem is 25. Now, the other thing that you've technically done is you've taken this polynomial and you've divided it by x minus 3 to get a result of x squared plus 6x plus 6 with a remainder of 25, but that's not what the question asked. The question just wanted you to evaluate the problem at 3. Plug a 3 into the function. That's all it wanted you to do. And the result was 25. Oh, happy day. Let's take a look at a different problem that's asking you to do something completely different. Let's say, ooh, that's an interesting one. Haha. Okay. Yeah, let's do that one. I want to do that one. There we go. Example, find all real solutions of x to the fourth minus 6x squared equals 27. They want you to find the real numbered solutions of this problem. Awesome. Fantastic. So we got, check what my battery life is right now. Hold on. Crikey. Yeah. Yikes, I gotta plug that thing in. Will this reach? I don't think it'll reach. Regardless, I'm almost done anyway, so my second camera is on my phone, and I have to actually charge that thing. I've been using it all morning. So, but to solve said problem, first and foremost, as we've been doing from the beginning of the school year, you need to get one side of that problem equal to 0. You have to get one side of that problem equal to 0. You have to. Next, I'm going to take a look at the graph. With a problem like this, it is best if I know where to start. And the best way to know where to start with a problem like this is to look at the graph and see if I can't visually identify any zeros in the function, as we've been doing. And it looks like there are 2 that I might be able to identify right now. It only looks like 2, though. It says find all real solutions, and I'll be able to confirm whether or not the result has only 2. Again, according to our definitions, it should have at most 4 real solutions, the rest being made up of possibly repeated and complex. I don't know, let's see what happens. Looks like 3 and negative 3. Let's do it. 3 and negative 3. Mind you, if my phone camera actually does end up dying, that is okay. I can still finish this lesson because my webcam would still be live. So don't worry about that. I'm going to keep going with this. 1, 0, negative 6, 0, negative 27. With this problem, I have to put in the placeholders for x cubed and x. You have to. It looked like 3 and negative 3, so I'm going to try 3 first for funsies. 1 plus nothing, multiply. 0 plus 3, multiply. Negative 6 plus 9, multiply. 0 plus 9, multiply. 27. Ah, perfect. Now, it also looked like negative 3 was the solution. Now, I've taken this 4th degree polynomial, I've divided out a 0 of the function, oh happy day, and I've gotten it down to this. I also would like to divide out that negative 3. Now, I don't need to include the remainder in the next level of division. I don't need the remainder. 1, multiply, multiply, multiply. Nailed it. Now what's interesting about this result down here at the bottom, remainder, constant, x squared, it results in an x squared plus 3, which, if you looked at an x squared plus 3, it has no remaining real solutions. There's only 2 real solutions then. How do we know where and when to add placeholders? Good question. Very good question. In this original problem, the degree of the polynomial is a 4. The largest exponent, it's x to the 4th power. It is missing an x cubed. Thus, you have to put a 0 in as a placeholder. The answer is whenever it's missing a term. Then it does have an x squared term. Yay, it has an x squared term. But then it's missing an x term. And since it's missing the x term, you have to put a 0 in as a placeholder. And then it has the constant. Oh, happy day. This has no remaining real solutions. Thus, my answers are going to be x equals 3 and x equals negative 3. Those are the solutions that I was able to prove. I was able to prove, look right here, there's the 0. I was able to prove that that is a 0 of the function, and that is a 0 of the function, the negative 3. Thus I circled them, and I said, oh, happy day. Where's my phone battery at? 6% now. Great. That's great. Okay. I would like to do one more example with you. Yes, one more example with you. And then I'm going to call it a day on this one, because I only have you for about 10 more minutes, but I'm not going to take you all the way down. Example, factor completely. And, oh, I don't like that example. I'm going to pick a different one from over here. Ooh, that's a fun one. Let's do that one. F of x equals x cubed minus 2x squared minus 11x plus 12. Double check, yes. I'm going to factor completely. Well, Mr. Markey, how do we even start this problem? I don't know. How about you graph it and take a look at what it looks like? Because if you can visually identify any zeros, you can divide out using synthetic division. Looks like negative 3, positive 1, and positive 4. We'll start with the 4. I'm just confirming, that's a 2, that's a minus 2. I'm confirming that this positive 4 actually does indeed work. 1, 4, 2, 8, negative 3, negative 12, 0. Yes, it does. You've confirmed that x minus 4 is a factor. You've confirmed that x minus 4 is a factor because x equals 4 is a 0. Let's continue with it. But I'm only going to continue with those numbers. I'm not going to use the remainder. Why would I use the remainder? It looked like positive 1 also worked. 1, 1, 3, 3, 0. It does indeed work. You have proven that x minus 1 is a factor. Now, remainder, constant, x, technically, you do have x plus 3 left over. You could continue with negative 3 as the remaining 0, but you don't have to, because you already have x plus 3 as the remaining factor. Remember the definition that I gave you. If f of k is equal to 0, I've given you this definition in the past. If f of k is equal to 0, meaning k is a 0 of the function, then x minus k is a factor. That's the definition that I've given you. Which means if I had to factor this thing completely, there it is. If I needed to give you the zeros of that function, it'd be positive 4, positive 1, negative 3. If I were to look at this graph, now the graph is a bit off the screen. That's okay. It has exactly 3 zeros. It has at most 3 zeros because of the degree is a third degree polynomial. It has 2 turning points, which also fits the definition that I gave you earlier. All of this stuff is all-encompassing. It's so great. I love it so much. Okay. So, your job. There is an edge elastic assessment that you need to get done for me. Let me switch to widescreen just because it's fun. Yay, there I am. You have an edge elastic assessment to get done for me. I don't like it. I'm too big. Hold on. Top down. There we go. It's due Wednesday. I need you to pay attention to that due date. I need you to get it done. Take your time with it, but get that thing done. And don't forget to click submit when you're done. If you have any questions, you can email me, and I'll get back to you. I'm going to be live streaming from home the next few days. Don't have to travel. Next week, I should be back in my classroom. They said, like, hey, next week teachers can go back to their classroom. I secretly hope I can just stay home because I have a much better setup here than I do in my classroom. In my classroom, there's a giant glare on the screen. I'd much rather do this with you guys. But don't forget to subscribe to my personal YouTube channel because, you never know when I'm going to be playing video games next. I don't know. I wanted to play Mike Tyson's Punch-Out, but I'll have to see if I have time today because I have so much work to do for actual job rather than my YouTube job. But anyway, thank you guys so much for joining. I'm going to let you guys go a few minutes early. Don't tell anyone. I don't care. But like I said, if you have any questions, email me. I'm going to have to be doing this live stream thing for parent-teacher conferences today. Oh, man. I know. It's going to be fun. All right, guys. I will see you next time. Goodbye.